this weekend, my daughter was having some sort of allergy symptoms, and so I had to go to the store. I'm wearing my pajama bottoms and flip-flops, walking around looking for some antihistamines or something for allergy symptoms. And when I got to the section of the store, the grocery store, a lot of the shelves, half the shelves were empty. I couldn't believe how poorly stocked things are. And maybe this is just the way things are now with inventories. What was frustrating to me is that they were out of the generic brands. And so I ended up being forced to buy, some 1990s, 30 years old drug, which is probably fine. Allegra. Had to buy the fancy brand instead of the generic brand. And it's like $1 a pill. I couldn't believe it. Why am I paying $1 a pill for something that's off patent and 30 years old? But I wanted to talk about this compound fexofenadine, which is the active ingredient. There's a lot of these, Claritin, Allegra, they all are probably pretty similar. And let's take a look at the structures there. For what is fexofenadine? It's actually the hydrochloride salt that they sell you. So these are the pills that are inside that bottle of Allegra of fexofenadine. And what's interesting is when you look at the chemical structure, the pill itself is completely uninteresting, but the structure of fexofenadine immediately draws your attention. And you can see in here there's bonds that you know how to make. You could probably figure out how to synthesize this whole compound based on chemistry that we've already shown you in this class. I'll talk about this in just a second, but these two bonds right here, that comes from Grignard reagent addition to an ester. This bond right here, that's SN2. This bond right here comes from aryl lithium addition to an aldehyde. We already know how to do that. You can probably guess that this bond right here comes from some sort of electrophilic aromatic substitution. I mean, these are all reactions that you should already know how to do. Let's go ahead and take a look at the first step in the synthesis of fexofenadine. Should be very familiar to you. It's exactly the stuff that we've just been talking about last week, the stuff that we're working on in discussion section. And the first step in the synthesis of fexofenadine is you take an ester. But it's a little bit tricky here because in this molecule that has the ester also unfortunately has an NH. It is not easy to deprotonate that NH. But aryl lithiums and Grignard reagents are so basic, they will react with that NH. We normally wouldn't do this in our class, but they add an extra equivalent of phenylmagnesium bromide. Notice they're adding 3 equivalents here. One of those equivalents is deprotonating, and the phenyl anion basically deprotonates the H and makes phenyl H, benzene, and that just evaporates at the end of the reaction. So once this is N-, it doesn't react. The other 2 equivalents, there's 3 equivalents of the Grignard reagent. The other 2 equivalents of the Grignard reagent are adding in to this carbonyl group. So the first equivalent of the Grignard reagent adds in, makes a CC bond. That's right here. And so now you end up, I'm not showing the whole mechanism, so then you make a phenylketone. That's more reactive than the initial ester. You can't stop at the ketone stage. You can't just add 1 equivalent and stop at the ketone stage. Nothing you do will stop it. If there's any more molecules of phenylmagnesium bromide in there, they will add to the ketone faster than they add to the original ester. And so you end up with that second bond right here. So you end up with 2 phenyl groups. You end up with a tertiary alcohol. That's kind of indicative. When you have 2 of the same group attached to a tertiary alcohol, that's classically synthesized by adding Grignard reagents or alkylithiums to esters. And the ethanol byproduct you get, that all gets protonated and the ethanol evaporates. They evaporate that off at the end. This is the way they make fexofenadine. Same chemistry we're learning in this chapter 17 here in our course. All right, let's go ahead and continue on. We're almost done. We are almost done with chapter 17. Chapter 17 is about hydrido reagents, adding them to carbonyl groups, and adding carbon nucleophiles to carbonyl groups. Organomagnesium compounds, organolithium compounds, and I showed you that we could add to carbon dioxide just like any other carbonyl group. That's a way to make carboxylic acids. And I told you you have to work that up with hydrochloric acid. You can't just use water. Water is not acidic enough to protonate a carboxylate anion. Now there's one class of organometallic reagents that's special, and it's a little bit obscure. It's like, I'm not even sure why they put this You know, it's just not that common, but it's worth talking about because it presages more chemistry that we're going to see. And this other class of reagents that we have not yet talked about are referred to as cuprate reagents. Cuprate. Let's take a look. Cuprate. That ATE ending tells you there's going to be a negative charge on copper. You don't know anything about this reagent, but you know it's going to involve copper, and there's a negative charge on copper. And if there's a negative charge on copper, all the bonds to copper are nucleophilic. If there's a negative charge to boron, all the bonds to boron are nucleophilic. If there's a negative charge to aluminum, all the bonds to aluminum are nucleophilic. Aluminate, borate, cuprate, it's kind of this similar theory here. Okay, so I want to talk about what happens if you take an alkylithium or a Grignard reagent and you add those to this type of reactive functional group. And let's go ahead and mark out what is it that is distinctive here. We would refer to this as an enone or an alpha-beta unsaturated enone. And we'll tell you about the numbering of these positions later. 1 carbon away from the carbonyl is called the alpha position. 2 carbons away is called the beta position. That's exactly the same lettering system they use for amino acids. They're called alpha amino acids because there's an amino group at the alpha position of a carboxylic acid. So you might have learned about those in your biochemistry class. So when you take an enone, an alpha-beta unsaturated with a double bond at the alpha and beta positions, an enone, and you react it with an alkylithium or a Grignard reagent, you get exactly the reaction that we've been showing you the whole time. So let me go ahead and draw this out. So if I take an alkylithium reagent, it could be methyllithium, ethyllithium, butyllithium, phenolithium, and then we follow this up with an H2O workup, right? You end up forming a new bond right here. Here's this new bond that you make. So you already know that. That's nothing new about that. You don't have to memorize anything new. But here's what's surprising. If we take these other reagents that you have not yet seen before, these cuprate reagents, and let me go ahead and show you the way we draw these out in a text form to conserve space. I'll show you the structure in a little bit. We draw the cuprate reagents like this. R2. There's 2 R groups to the metal, right? Not 1 R group attached to magnesium or 1 group to lithium. It's 2 R groups attached to copper, and then there's a lithium associated with that. So that's a cuprate reagent. There's 2 R groups attached to copper, and there's a lithium. And we follow this up with an H2O workup. So you can see, if I come back over here, when we did the addition to the carbonyl, we ended up with an R group, a new carbon-carbon bond, and an H that came from the workup. That's what we've been doing this whole chapter. You make a bond to the carbonyl, and then you end up protonating the alkoxide during the workup. And if you number the carbons in this enone system the way I've shown you here, 1, 2, 3, 4, 1, 2, 3, 4, adding to the carbonyl is often referred to as 1,2 addition. I mean, do I care that you know that it's called 1,2 addition? You could just say adding to the carbonyl and everybody would understand what you say, but the book likes to introduce this nomenclature because later we're going to see a similar pattern for this cuprate reagent. The cuprate reagent makes a bond to carbon 4, and so we refer to that as 1,4 addition. And you'll see mechanistically where the atom 1 comes into play. What's not at all obvious, I don't think, is that where did the H from the workup go to? The H from the workup did not end up attached to the oxygen. The H from the workup ended up attached here. And we don't draw H as attached to carbon. I'm drawing it here so you can see it. So now you get to see this looks quite a bit different from what we've been doing for the rest of the chapter. So let's take a look at this. You know, it's quite valuable to put substituents at this 4 position of an enone. There's plenty of drug molecules that are made using this type of chemistry. Let's go ahead and talk about the mechanism for this reaction. What's going on mechanistically when you use cuprate reagents? So if I take a cuprate reagent, let me go ahead and draw out the cuprate reagent over here. I'm going to, it doesn't matter whether R is methyl or ethyl or phenyl. This is the structure of a cuprate reagent. 2 bonds to copper. 1 bond to copper is neutral. If you make a second bond to copper, what they do is they take 2 equivalents of alkyl lithium and they add it to copper bromide, and so you precipitate out the lithium bromide. And I'm going to draw this in a charge separated form. you don't need to draw a bond between copper and lithium, although there's certainly interactions there. And so there's a negative charge on copper. It's a cuprate. That means those R copper bonds are nucleophilic. And you could never have guessed this if I didn't tell you. But those R copper bonds selectively react not with the carbonyl. They add to that 4 position of the enone. And let's push the arrows. I'm going to take that nucleophilic R copper bond here, add it into the carbonyl, and I'm going to push these electrons all the way up to the oxygen, like that. That's why they call it 1,4 addition. Right? You end up with a negative charge on atom 1 of that 4-atom system. So sometimes we refer to this as conjugate addition. We'll talk about that nomenclature later, so I might use the word conjugate addition because the double bond is conjugated to the carbonyl. But you can see that makes this bond to the number 4 atom of this 4-atom system. And so we end up generating this enolate, a type of, or this intermediate that we're going to see a lot more called an enolate. Boy, this is going to be the stuff of chapters 21 and 22 is all about these enolates. And you haven't seen these before. I don't think you've seen these before. But we're going to see more of these enolates. Let me write that down. It's such an important word that I'm going to be using a lot later. Maybe not so much for this chapter, but we're going to have entire chapters on enolates. Now, when you put these into an aqueous workup, you're going to put a proton on the carbon atom. And to help you understand why you protonate the carbon atom, let's draw out a resonance structure for this. I'll go ahead and draw a resonance structure where I take these electrons and I push the electrons onto carbon like that. And now you can see why you protonate on carbon. This other resonance structure of the enolate is kind of indicative of why you protonate. These are just different representations. This resonance is not a chemical reaction. I'm just drawing the same enolate 2 different ways. It's an enolate either way I draw it. It's the same molecule, just representing it 2 different ways. There's some negative charge on oxygen. There's some negative charge on carbon. When you protonate this in the workup, you end up adding an H to the carbon atom. And so hopefully acid-base reactions are not really new for you. And so that's what leads to 1,4 addition. All right, the book has some review reactions, just reviewing stuff that was in the chapter in these other sections. And there's a lot of material in this chapter. That's why we're spending time on this in discussion section to go over these reactions. And, you know, you can fault me for loving carbon-carbon bond-forming reactions, but chapter 17 is really the stuff of Chemistry 51C. It's the stuff of organic chemistry. It's the way we make drug molecules and bioactive molecules using the tools of organic chemistry. You have to know these chapter 17 reactions. Okay, but we're not going to stop here because we've got 3 more chapters on adding stuff to carbonyls and nitriles, which are analogs of carbonyls. So let's go ahead and take a little breather here and let's get ready because we're charging into chapter 18 and I'm going to give you more chemistry to know, more reactions that you need to know how to use to solve the problems that will be on our next exam. So let's go back to that and get ready for chapter 18. This is chapter 18. Now you'll recall that chapter 16, the aromatic substitution chapter, the aromatic reactions chapter, I gave you an overview and I said you have to know these 5 recipes. Well, I got 5 more recipes you have to learn for this chapter. And you may think, again, like, oh, 5 recipes, that's easy. It's not so easy, right? Think of how hard it was to learn all that stuff with reacting with benzene rings. It's not so easy. So let's go ahead and take a look at these recipes that we're going to cover here. I feel like, you know what? I feel like I had a chance to review something and I might have missed something in the last, I'm just now looking. So if you're wondering, wait, wasn't there another page on the end of this? Yes, there was another page. Sorry. Let's go back. So I just wanted to review conceptually some powerful transformations, 2-step transformations, like synthetic sequences that are common and that are totally perplexing if you have not seen them before. So let me just ask here, or just pose this scenario where, let's suppose that you were asked for how to make a carbon-carbon bond here. There is no one-step method for you to add a new carbon-carbon bond there. And if you're looking at what happened, I hope you're seeing it's not that you just formed a carbon-carbon bond. You removed an H. Right? You need to see that that's as important for you to see that you removed an H as it is for you to see that you formed a carbon-carbon bond. And so what is the two-step method that you would traditionally use to do this? Well, if you want to form a carbon-carbon bond right there, we need a carbonyl. I just showed you a whole chapter worth of adding nucleophiles, carbon nucleophiles to carbonyl. So how do we change this to a carbonyl? There's one reagent that is super powerful for that, and that is pyridinium chlorochromate, PCC. I'm not asking you to learn the structure. It'd be great if you did. I'm not asking you to know the mechanism for pyridinium chlorochromate oxidation, but you need to know that PCC will take a primary alcohol to an aldehyde. Now we can form carbon-carbon bonds with that. And do you know how to make carbon-carbon bonds with methyl? We could add methyl lithium, we could add methyl magnesium bromide, methyl magnesium iodide. I'll do methyl lithium here because it's fewer letters to write. There we go, carbon-carbon bond. And we've got to protonate the alkoxide product that we get, so we use a workup here. And you just have to be used to enumerating those steps. Step 1, methyl lithium. Step 2, water. There was no one-step way to do that reaction. You have to know this two-step sequence. And if you haven't practiced this, it's just going to seem completely perplexing. How do I make a new carbon-carbon bond next to an alcohol? There's going to be a related transformation where we're going to ask you to do things like this. We're going to ask you, oh, how do you take an aldehyde and add a group to that? What's happening there? You're removing an H. You're replacing an H. I hope you can see that you just lost an H in that transformation. That's just as important as seeing that you made the new carbon-carbon bond. Now here we already have a carbonyl, so we can add our organometallic reagent directly. So let's go ahead and add that organometallic reagent. We could add phenyl magnesium iodide, phenyl magnesium bromide. Again, I'm just going to write phenyl lithium because it's fewer letters for me to write here on my page. And then step 2, guess what I'm going to do here? Is anybody mystified as to what step 2 is going to be? It's going to be a water workup. And you'll find as we go along, I stop writing the word workup because, right? Why was I showing you the word workup initially in this class? Because I wanted you to know I'm not adding water to do SN2 reactions or some other thing from chapter 9. But now that we're familiar with it, the water just adds a proton to stuff. I'm not going to write the word workup anymore. And so this makes a bond to where the carbonyl was. It adds that phenyl group on there, and the water workup puts that proton on the H. So there's no one-step method to convert an aldehyde to a ketone like this. You have to do this in 2 steps. So if only there were some special reagent we could use to oxidize alcohols to carbonyls. Now probably from the reduction oxidation chapter you might have learned things like, oh yeah, potassium dichromate, sulfuric acid, water. Yeah, that's too much work. Watch this. Look how easy that is. So easy. There's only special situations where you need that whole chromic acid oxidation thing, and we'll cover that when we get to chapter 19. But for now, PCC is money because, right, everything's about adding to carbonyls, so you need to know how to make carbonyls from alcohols. PCC. There you go. Okay, so chapter 17. Know how to make bonds to carbonyls by adding organometallic reagents. And hydrido reagents if you want to make HC bonds or reduce carbonyls. Okay, now we're ready to go to chapter 18. I apologize for that little blip there. What are our recipes for chapter 18? Next chapter. I'm going to teach you 5 recipes. You have to know these. You have to know how to apply these to any substrate I give you, whether it's a steroid with 40 atoms or cyclopropanone with 3 carbon atoms, or acetone. You need to know how to apply this in every conceivable situation. So let's go ahead and take a look at this first set of conditions. You'd think that this ought to be something you've seen before. It looks a little bit like adding acetylide anions to carbonyls. So why do I need to cover it in this chapter? Let me show you the recipe for this. A cyano group is not an acetylide anion. And our recipe here is we take sodium cyanide which is poisonous. Cyanide is a modest poison. And we do this in HCl. Now notice there's no number 1 and no number 2. You've got cyanide anion floating around in the presence of HCl. You could never do that with acetylide anion. But here you don't if you enumerate it, it's wrong. You actually have to have all mixed together, sodium cyanide powder and hydrochloric acid mixed around. And this makes a functional group that we'll talk about called a cyanohydrin. Makes a carbon-carbon bond, but it's a special carbon-carbon bond. Cyanide anion is not like Grignard reagents or organolithium agents. Okay, so that's one kind of oddity that maybe you might think it belonged in the last chapter, but it kind of belongs in this chapter. Second transformation you need to know is how to take a CO double bond, like a ketone or an aldehyde. Not esters, not amides, not acid chlorides. Ketones and aldehydes. That's the theme of this chapter. Ketones and aldehydes is what we're talking about this chapter. Ketones and aldehydes. So R here is carbon, or it could be an H molecule. So how do we convert a C double bond O into C double bond N? Well, this is pretty easy. We just need to take an amine that has 2 H's on it. There we go. R prime can be methyl, R prime can be isopropyl, R prime can be phenyl, R prime can be butyl, R prime can be cyclopentyl. You get the idea. Now this isn't enough, right? I hope you can see that in this reaction, we're going to lose an O and we're going to lose 2 H's. We're going to have H2O as a byproduct. Now I'm not going to draw the H2O, it's not interesting. But to make this reaction work, you need to add one more thing, and it won't work if you don't add it. We need to add a secret acid catalyst that is so secret the book doesn't want to tell you. They say weak acid because the book doesn't seem to understand the difference between low concentrations of acid and acids that have modest pKa's. So I'm going to just tell you what that secret acid is. Boy, it's super secret. It's acetic acid, vinegar. Let me just, I'll write it out the way we write. ACOH, and I'll talk about that abbreviation. Acetic acid. They just did not want to tell you that. I don't know why. If you ask any chemist, what do you use for making this functional group called an imine, they would say, oh, catalytic acetic acid. That's the #1 choice. Okay, there's another weird functional group. This one is hard to remember. And it's actually quite similar, but it's hard to remember. And I'll show you why it's not similar, why it's similar. You can see what we're doing here is we're losing an oxygen atom here from a carbonyl. But in this case, there's 2 differences in the recipe. One is if we take an amine that only has 1 H on it, so that has 2 different R groups on there and only 1 H. And if you take a ketone or an aldehyde that has at least 1 H at this carbon neighbor, that's the recipe. You need an amine that only has 1 H, and you need to have an H attached to the neighboring carbon atom that's next to the aldehyde or ketone. And without those, this won't work. And when you do that, you make a double bond, but it's not a CN double bond. What you'll see is you're making a CC double bond. That's like an alkene. And so we don't call this an alkene because there's an amine attached to it. They've come up with the clever name called enamine, like it's an alkene with an amine attached to it. Pretty sensible. And so you could see the atoms that are lost here. You're losing an oxygen, you're losing an H from that carbon next to the carbonyl, and you're losing an H from the N. So obviously you're driving off water as a byproduct. Water is a byproduct in this case. And we need we're not going to talk about this, but you usually have to do something special to drive the water off of the reaction. Again, this needs a catalyst. And it is a catalyst that is so secret, the book doesn't want to tell you what the catalyst is. Guess what the catalyst is? It's the same, it's acetic acid, it's vinegar, same secret catalyst they don't want to tell you. I think they think it's just too mind-blowing that you're adding vinegar as a acetic acid as the secret catalyst here. Okay, so imines and enamines. You're going to need to know those transformations. The enamine, I feel like, is the hardest one. Now, we're going to show you a reaction where in one step, you can take aldehydes and ketones, C double bond O, and convert those C double bond O's into C double bond C. So, and this is a mysterious reagent we're going to end up talking a little bit more about. We'll have to talk you through the mechanism. You've never seen anything like this. We take this type of reagent called a Wittig reagent. You're going to be doing something like this in the 51LC laboratories. It's not exactly a Wittig reagent, but a similar phosphorus-based reagent. This Wittig reagent, it's a phosphoniumylide, has triphenylphosphine, 3 phenols on phosphorus, and that is double bonded to some sort of carbon atom that has 2 groups on it, H and an R. And if you do that, you'll end up with a new carbon atom that has an H and R prime. So we'll talk more about these, and that's going to freak you out because you're thinking, wait, isn't that 5 bonds to phosphorus? You can't have 5 bonds to phosphorus. Of course you can have 5 bonds to phosphorus. That's DNA, RNA, it's all 5 bonds to phosphorus. Phosphorus is not a second row atom, it's a third row atom, so no problem with 5 bonds to phosphorus. Get over it, we'll get over that. Okay, so that is a great way to make alkenes. But there's just kind of exceptions and weird things to know about this alkene forming reaction, this olefination reaction we call the Wittig reaction. Okay, our last functional group that we're going to teach you how to make is to change a C double bond O into 2 single oxygen bonds. And we have a name for that functional group. It is called an acetal. This functional group where you have an sp3 carbon and 2 oxygens attached is called an acetal. And that is intrinsically unstable. Each oxygen wants to push out its neighboring oxygen. You touch that with acid, poof, it's gone. It's back to a carbonyl. So as soon as you make an acetal, unless they have some special stabilization feature, they really want to go back to carbonyls, right? C double bond O is the driving force in organic chemistry. Reactions want to go back to C double bond O. Carbon dioxide is like the driving force for metabolism. It's the driving force for global chemistry. CO2 formation is the big problem that we face. And so all these reactions where you react CO and remove the C double bond O, you're kind of going uphill if you don't remove something from the reaction or make a more stable product. So what's our recipe here? Our recipe is that we're going to take alcohol. Now we need at least 2 equivalents of the alcohol. You can kind of see that. And if you look carefully, you can see we're going to lose 2 H's from the ROs and then 1 oxygen from the carbonyl. We're going to lose H2O again. You have to drive water out of the reaction to drive the equilibrium here. I'm going to write the word excess because 2 isn't fast enough. 2 doesn't have a good enough equilibrium constant. So you have to use a big excess to drive the equilibrium constant using Le Chatelier's principle. You just put a ton of alcohol in there. It drives the equilibrium towards the acetal. Now we need an acid catalyst in this. And you're thinking, oh yeah, acetic acid. Unfortunately, in this reaction, acetic acid is not acidic enough. And we'll explain that later. We need a powerful acid here. And the one that we commonly use for this transformation, we'll talk about in more detail later. It's toluene sulfonic acid. It's a benzene ring with a sulfonic acid functional group. And you might be saying, hey, didn't we learn how to make sulfonic acid benzene? Exactly. They make this on an industrial scale using chemistry that you learned in chapter 16. All right, let's go ahead and take a look at these at carbonyls. I want to kind of, in a way, step back a little bit because at the beginning of the last chapter, maybe I should have spent more time talking about why are carbonyls reactive and how to think about them, and maybe some naming principles. The kind of first section of the book tends to give you some introductory stuff about reactivity. And so this is a good chance, even though we didn't do it at the beginning of the last chapter, to talk about different carbonyl compounds, specifically aldehydes and ketones. That's this chapter. This chapter is not about esters. We're going to have a whole nother chapter about esters and amides. This chapter is aldehydes and ketones. And I just want to point out the relative reactivities of aldehydes versus ketones. And then there's one very special aldehyde, formaldehyde. So when you put more carbon atoms on carbonyl groups, so if you take these carbonyl groups here, the more carbon functional groups, more alkyl groups I put on there, the less reactive the carbonyl becomes. It's not 1 billion times less reactive. It's not a million times less reactive, but the reactivity changes enough where you could actually, in theory, add to the more reactive one in the presence of the less reactive ones. Now, why should there be this order of reactivity? Why should it be easier to add to formaldehyde? Why is formaldehyde more reactive? Why is an aldehyde more reactive than acetone, than a ketone? And to help us understand that, what we're going to do is we're going to draw resonance structures of each of these and think of them as carbocations. Because you should already know something about the relative reactivities of carbocations, depending on how they're substituted. So if I draw these resonance structures, these aren't different molecules. They're just different ways of depicting these same molecules. Well, let me not draw the atom C. I'll just... So if I draw these resonance structures based on my arrow pushing, I'm taking electrons away from the carbon. Well, that's a carbocation. And now let me do the same for this aldehyde, acetaldehyde. That's a carbocation. Let me circle the charges because it's not obvious. When I draw that line, you might be thinking I'm drawing a methyl, so I'll circle that charge because it looks too much like an oxygen-carbon bond. And then I'll come over here and I'll draw the resonance structure for this ketone, for acetone. And this resonance structure is a carbocation. And you already know something about the relative stability of carbocations, right? You should already know that carbocations with 3 substituents, tertiary carbocations, are more stable. They're more stable than secondary carbocations. I'm going to write most stable if you compare these. And just a primary carbocation should be the least stable. And for carbocations, more stable carbocations are less reactive, right? Let me go ahead and draw that in a blue pen here. More stable carbocations are less reactive. So if you think of carbonyl groups as carbocations, then it's easy to understand this order of reactivity. And I expect you to know this order of reactivity. They ask you these questions in the book. You know, on my exams, sometimes I have these things, draw a circle around the most reactive or the least reactive. This principle is going to turn out to be important. And it'll be much more complex as soon as we mix into this, thinking about esters and amides and acyl chlorides. Those will make this simple thinking seem additionally complex. Okay, so aldehydes and ketones, that's this chapter. We're going to be taking aldehydes and ketones, using these recipes and adding nucleophiles to the aldehydes and ketones. Okay, the book always starts off by asking you about nomenclature. I will never ask you an IUPAC nomenclature on my exams. Now, I just had to make a decision. We don't have enough time in this class to ask you everything. Sometimes the standardized exams, MCAT, DAT, those types of exams might ask you some IUPAC nomenclature question. But I promise you, if I take the top 200 list of prescription pharmaceuticals in the United States, you could never in your lifetime give an IUPAC name to those structures. And I probably couldn't do it on my first 10 tries either, so I don't feel like I'm teaching you anything with IUPAC nomenclature. But I do expect you to know the names of functional groups, right? Functional groups, we need to be able to talk about functional groups, acetic acid or things like that, and have a shared conversation. So let's go ahead and talk about this general concept that I've already mentioned before. We've talked about Friedel-Crafts acylation and this concept of an acyl group. I expect you to know what an acyl group is. That's this attached to anything. Could be an acyl chloride, the acyl group could be attached to a cyclohexane ring, the acyl group could be attached to a benzene ring. X can be anything here, and we call that an acyl group. Acyl. Now I expect you to know the names of 2 very specific and very common acyl groups. The functional groups. I expect you to know the names of these functional groups because they are so common. And the first functional group I expect you to know is acetyl, because it is such a common functional group. And the second one I expect you to know is called benzoyl. Not benzyl, benzoyl. Totally different from benzyl. Okay, let's take a look at an acetyl functional group. An acetyl functional group is pretty simple. It's about as simple as you can get. It's just this. It's like a methyl acyl. It's an acyl group with a methyl group there. That could be acetic acid. That could be acetamide. That could be acetylbenzene. That's actually called acetophenone. So that's an acetyl group. And you have heard of acetyl before if you've taken any biochemistry class till you're sick of it. Acetyl-CoA, right? Haven't you guys had to sit and memorize these stupid pathways that you're never going to use again? Talking about acetyl-CoA and how many acid, you'll never use that again. I guess if you go to medical school, they'll ask you that more, but nobody on this campus does research on that. Okay, so what's another common functional group where you just plain need to know the name of? That is a benzoyl group. It is not a benzyl group. So if I attach this to something, that's called a benzyl group. But if I put a carbonyl here, that is a totally different functional group. That's a benzoyl group. A benzoyl group is like benzoic acid. That's what they put into Coca-Cola as a preservative. Or benzamide, or I guess I could call that benzophenone. This is a benzoyl group. So when you attach that to things, you would say that phenyl with a carbonyl is a benzoyl group. You've probably seen benzoyl peroxide in acne medications. I don't know if you've ever looked at the, right, benzoyl peroxide. There's an oxygen-oxygen bond between two benzoyls. Yeah? X is anything. So this could be, I'll just write any here. So that could be carbon, that could be phenyl, that can be amino, that can be OH, X can be anything. But the thing in the box is called an acyl group. R on the other side can, R can be anything and you call it an acyl group. So over here, R acyl is kind of the generic name. I see what you're saying. So what's this? That can be phenyl, methyl, isopropyl, ethyl, cyclohexyl, and you still call it an acyl group. Acyl is the generic name when R is some kind of an alkyl. R can't be a heteroatom, right? R is something with carbon there. So something with carbon. Let me just, sorry, that's what you, carbon. That's some sort of carbon-based thing. Okay. Aspirin is acetyl salicylic acid. There's an acetyl group in aspirin. Okay, so I expect you to know acetyl and benzoyl, but IUPAC nomenclature, not really, no. Well, I mean, great if you learn it. I hate to tell you don't learn anything, don't learn something that's in the book. I'm just going to tell you I won't put that on my exams is where, so feel free to learn all about the IUPAC nomenclature. Now, what do I put on my exams? Right? If you've looked at my, some people ask me, do I have to know spectroscopy for the next exam? I'm never going to tell you what I'm going to put on the next exam. Don't ask me what's going to be on the next exam. It's not ethical for me to tell you and not everybody else. But if you look at my past exams, I'm not a real creative person. There's usually a spectroscopy question on every exam that I've put in the past. And we haven't had a chance to go through spectroscopy. For some of you, it may have been 2 years since you covered any spectroscopy, and I want to tell you how to approach spectroscopy problems, just kind of in general, and carbonyls are an important feature of many spectra. So how do you use spectroscopy? You always use spectroscopy in the same way. We use spectroscopy to rule out implausible structures. You need a list of structures. That's the way to approach spectroscopy questions. Sometimes I give you a list of structures. Those are the easy ones. Other times I give you a set of reaction conditions and you have to say, well, there's 5 plausible products here. E2 elimination, SN2, SN1 products, and you need to draw those out and then eliminate the ones that don't fit. That's harder because it requires you to anticipate what are some of the possible side products. So here's how you approach a spectroscopy problem when you've got a set of plausible structures. Let me tell you that the first thing you should always do with spectroscopy problems is use the easiest data first. Cross out as many of these possibilities using the easiest things first. And so what is the easiest piece of data that you always have, or not always, that you could possibly have in spectroscopy problems? That would be the molecular formula. Anybody can use a molecular formula. You don't need to be some advanced organic chemist to know how to use a molecular formula. So if I look at this molecular formula and I see that it contains a nitrogen, well, I'm going to cross out every structure that doesn't have one nitrogen atom. So here we go. Bye. One nitrogen, one nitrogen, one nitrogen. Okay, all the rest. So I've already eliminated one of them, and all I needed to do is look at the molecular formula. Okay, it should all have 2 oxygen atoms. So anything that doesn't have 2 oxygens, looks like all the rest have 2 oxygens. Now anything that doesn't have 5 carbons, I'm going to cross out. So look at this, benzene ring. That has 6 carbon atoms. That can't possibly be correct. I'm not going to bother looking at the spectra. I'm not going to... Benzene compounds don't have 5 carbon atoms. Here's one over here. I better be careful and count them up. 1, 2, 3, 4 carbon atoms. That's gone. Right, see how much headway we're making, and we haven't done anything fancy with spectroscopy. So this is the approach you make. Wow, can you guys hear some thunder and rain? That's awesome. Wow, Southern California, who thought? Okay, so we're still going here. I don't even know. I think this adamantyl cage structure has more than 5 carbons. 1, 2, 3, 4, 5. Yeah, it has more than 5 carbons. Bye. Look at that. I mean, we haven't even started. So if you guys don't use the molecular formula and I give it to you, I'm thinking, right, well, how could you choose a structure that doesn't match the molecular formula? I'm not going to bother counting the hydrogens. That's too much work right now. Okay, what's the second easiest piece of spectral data that you can be given? It's C13 NMR. And you may be thinking, well, we didn't talk a lot about C13 in the lab or in my previous... That's the easiest data to use. My gosh, it has so much easy information in there. So, you know, the basic idea is that the number of carbons is the number of types of peaks. There's the number of peaks is the number of types of carbons, and there's none of this splitting business. You don't have to worry about singlet, doublet, triplet, that sort of business in neighboring whatever. Right? Go to that. Why spend your time trying to figure out splitting on proton NMRs? Go to the carbon first. And the other thing that's valuable about C13 NMR is the chemical shift ranges are very defined. Alkanes are in one region, benzene rings are in another region. Right? It just makes it more simple. Now, what's the third easiest type of spectroscopic information to use? That's infrared. Now, unfortunately, infrared is simple, but it doesn't have a lot of information. Right? IR will tell you there's a carbonyl, but can you really tell whether it's an ester or a ketone or an aldehyde? That's a lot of work. And frequently you can't know whether it's an ester or a ketone. So IR is simple, but it doesn't contain, there's a few easily identifiable functional groups, triple bonds versus carbonyls. And then the last piece of information is proton NMR. That's the hardest to use. So if they taught you to use that first, they're kind of screwing you because you just end up in this morass of data. Now, what is the easy part of proton NMR to use? It's the integrations, not the splitting. Don't look at the splitting. Avert your eyes and don't look at the splitting. Look at the number of H's. Oh, I see a 3H signal that integrates for 3H. That's a methyl. I mean, come on. Oh, there's a signal that integrates for 2H. You know, that's probably a CH2. Right? It's the last thing, you know, then you can kind of look at the chemical shift ranges. Oh, I think it may be a benzene ring, an H attached to a benzene. And the last thing you look at, the hardest thing to use, the thing that confuses everyone is the splitting stuff with doublet and triplet and singlet and septet and the neighbors, right? They put that out there to try to dupe you into using it first, but you gotta, you know, now that I've had years of experience, I love proton NMR because it is so complex. I love it. It's so complex and has so much information. But if I were you, you don't want stuff that's complex to use. You want stuff that's easy to use. Use the easiest information first. Let's go ahead and talk quickly about the C13 NMR. There are ranges here for C13 NMR. And I want to talk about these ranges. So over here in this range below about 110 parts per million, in this range down here, this is all the stuff that's singly bonded to carbon. Let me switch back to a black pen here. That's singly bonded carbon atoms. Oh, I didn't mean to draw an H. That has nothing to do with it. You have no idea what's attached to that carbon atom. Could be halogens, could be benzene rings, could be oxygens, could be nitrogens. You don't know, but it's going to be below 110. Singly bonded sp3 carbons. They're all below 110. Just count them up. Right, I come over here and I count them up. I don't have time. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12. There better be 12 singly bonded carbons in my structure, or I'm crossing out that structure. So easy to use. Okay, over here in this section, there's C double bonded to C. And I'm worried I think I have time here. C double bonded to C. In this section, about 160 parts per million to about, right, in this section right here, it's C double bonded to C. Now, unfortunately, you can't know whether that's just an alkene or whether it's a benzene ring. All you know is it's C double bonded to C. They all appear in that region, about 160-ish to about 110. Now over here in this range where we're about 155 to about 185, that's carbonyl groups, but not just any carbonyl group. We can be very specific. It's carbonyl groups attached to some sort of a heteroatom. So that could be oxygen, nitrogen, chlorine, acid chlorides, amides, carboxylic acids, not ketones and not aldehydes, but attached to a heteroatom in this defined range. Finally, when I get out here past about 185, that's aldehydes and ketones. They've got their own place in the spectrum, in the carbon spectrum, and that's pretty easy to use. So carbon NMR, very defined in terms of chemical shift ranges. That makes it much easier to use. There's no splitting in there you have to worry about. Just count the peaks. And the only thing you have to really watch out for is symmetry. Now I'll give you one last little tidbit here that is annoying. The beta carbon of enones will sometimes appear in this region that makes the beta carbon look like an ester. And there's no way around that. That's just a little fact you have to know. So in that region, like 160, 165, that beta carbon can look like an ester. All right, we're going to continue with aldehydes and ketones when we come back.